Hello IB. Today we're looking at 16C. So this part of the chapter on curve sketching looks at stationary points. We could define a stationary point as somewhere where the first derivative at that point is equal to 0. That means we're getting a horizontal tangent. Horizontal tangent. And we can see that this has happened so far when we've had a maximum or a minimum. So basically the point has gone up to a certain maximum, and it's sort of in some ways temporarily stopped, turned around and start coming down, or at a minimum it's gone down, temporarily stopped and then started going up again. It's an instantaneous change in direction. We're also going to find they occur at a point of inflection, and we'll go into that shortly. So let's first of all look at this sort of function. So here, this could be a cubic or it could be part of another bigger function, but in this case we've got a restricted domain. So we've limited our domain, and our domain we can see here in terms of the x's has gone from -5 to 6. They're coloured in circles, so that means those points are included. So we've got -5 is less than or equal to x, less than or equal to 6. So that's our restricted domain. So now when we want to talk about maxima or minima, we're talking about the y value. So the y coordinate tells us the value of the function and tells us whether we've got a maximum value or a minimum. We called this one a local maximum because it's reached up to a high point and then started going down, but it's not what we call a global maximum, because in this situation, this point here at the end of our domain has a higher value at 18 compared to this one where it's only 4. So they're both a maximum, but this is your global for the whole region, for the whole domain. This is the highest value that the function gets to, whereas here it's just a local maximum. The same story with a global minimum and a local minimum. Here the function goes down to a -4, so we're talking y values, before it starts going up again, but the overall global minimum is -16.5, because that's the lowest point it goes to. So whenever you're trying to find a minimum or a maximum, think local and global, and just check your endpoints of the domain to see what's happening. So if we had another function that, say, did, if I just do a set of axes here, and we had a function that, say, started at this point and then went up and then down and then up again, this point here, it becomes our global minimum, because not just a local but a global, because it has the lowest value. So the global minimum or global maximum could be either at an endpoint or within the function. So that's a global minimum. So minimum, maximum, we want to look at the y values. Let's now have a look at this next one here, which is looking at stationary points of inflection. So it's a stationary point, and remember we're using that term to say it has f-x equal to 0. So when we look at this cubic function, and if we take the first derivative, so if we differentiate this, first derivative is going to be 3x squared. And now if we make that equal to 0, so we want to see are there any stationary points, then 0 equals 3x squared. Divide both sides by 3, we get 0 still. So we get a solution to that is x equal to 0. So here we have, by definition, a stationary point. But if we look at our graph, here's our x equal to 0. We're certainly not at a maximum or minimum. But our definition is that our tangent to the curve at this point, at x equal to 0, is going to be 0. We're getting a horizontal tangent. So if we think about the tangents of this curve, we're going to have straight lines like this, a positive gradient, still positive but less, still positive but less, And at this point, the tangent to the curve is actually the same as the x-axis, and it cuts through the curve at that point. So up to here, the tangents have all stayed on one side of the function, but at this point, the tangent cuts through. And that's one of the features of this stationary point. So the tangent cuts through the function. So we call it a point of inflection because it's not a maximum minimum. That's just the term we use, and a point of inflection. We can see also there's a change of concavity. That's another feature. We see here we've got concave down, and up here it's concave up. So the curving upwards, curving down. So we're also getting, right down here, a change of concavity. So at this point, we've got our first derivative equal to 0. So if now I graph this, I wonder if it's going to go on nicely for me because I've got pen all over there. All right, so it has worked out well. So this function is our first derivative, so that's the red one, our first derivative, and this blue one here is the original function. So the red function shows us that it's got a positive gradient because it's above the x-axis, so there's our positive gradient, comes down to 0, it touches the axis there, believe it or not, and it still stays positive because the curve continues to be increasing with a positive gradient. So two different types of stationary points. In one case we can get maxima or minima, in the other case a horizontal point of inflection. So what happens to the sign diagram? If we have our minimum, that means we've got our curve doing something like this, and we have our tangent at the minimum, so that's where it's 0 on our sign diagram. What's the gradient going to be here? That's a negative gradient. What's the gradient over here? Positive. So if we see a sign diagram go from a negative value through a 0 to positive, we have a minimum. On the other hand, if we have a maximum and our horizontal tangent is at that maximum, then we've obviously got a 0 at our maximum. What's the gradient here? Positive. On this side, negative. So that tells us we have a maximum. Our horizontal tangent, this is what we had. We had a curve like this. Oh, no, let's try it again. It looked a bit like a cubic there. Well, it was a cubic. I want to try and make this point, I've exaggerated that a little bit. So here we don't have a maximum minimum, but our horizontal tangent, I'm now going to move that into place. All right, there's our horizontal tangent going through there. What do we notice about the sign diagram? At the point A, which is at this point here, then we have a 0 gradient at that point. What's the gradient beforehand? Positive. Gradient afterwards, positive again. Oh, another option here is if we had something that was coming the other way, going down, and here's our horizontal tangent through there. Well, that was lined up a bit better. At our point A, we have a 0, but in this case we've got a negative gradient, and on the other side a negative. So in other words, if we get a change of sign in our sign diagram, in other words the gradient's going from a positive to a negative or a negative to a positive, then we've got a minimum or maximum. If there's the same sign both sides, then we've got a horizontal point of inflection in these two cases. So here's a fairly typical type of question. Here's a function, and we want to find and classify all stationary points. if we've got x to the fifth and we've got a positive coefficient, then at a guess, we could have a function that's going up. Oh, let's go in black. We could have something that's going up, and we'll have 4 turning points. 1, 2, 3, 4. So if it's an odd power, it will always start and finish in opposite directions. So it could be something like that with 2 maxima and 2 minima. But we can't tell until we actually do the maths on it. So the first job is to differentiate it. So I've picked something so it cancels nicely. So we've got 5 times 5 comes down and cancels, so we get 6x to the 4th, so that makes it easier for us. Hopefully we remember how to do these differentiations. Minus 4 9s are 36x cubed plus 48x squared. All right. We now want to make that equal to 0 to see where the stationary points are. So we're going to equate f dash x equal to 0. So this equals 6x to the 4th minus 36x cubed plus 48x squared. Let's divide by 6 and make it simpler. So 0 equals x to the 4th minus 6x cubed plus, what are we doing, 8x squared. To solve this, let's now see if we can factorize it. So hopefully you can recognize all the factors there. Pull out our x squared, and we're left with x squared minus 6x plus 8. And you should be able to recognize that you can factor that even further. We've got x squared and x minus 4. You could have stopped the video and tried to do this without me going through it step by step, and then check your answers. So there we are, fully factored. Therefore, we have stationary points at x equal to 0, 4, and 2. So that's where we're getting all our stationary points. So immediately we're going, well, we've only got 3 stationary points. Our graph can't look like this, because this should have 4. So there's something strange happening in this one. All right, so let's now go through and do our sign diagram. So we know now that we can put on at 0, 2, and 4. We've got our 0 for our first derivative. So there's our stationary points. Now we want to test points in between. So you may want to stop and then have a go at testing these. Choose your points in each region to find out what's happening to them. So let's do the first one together. So let's test a point over here. Pick nice easy numbers. So I'm going to pick -1. And in class the other day, we looked at just doing a shorthand way instead of doing a full calculation. If I put -1 into here, then -1, let me just show you what we're doing in case we haven't all done it this way. -1, -4, -1, -2. So -1 squared. You don't need to sort of work them all out fully, but we can see that that squares to make 1. Then we've got times -5 times -3. The whole point is to find out, is it positive or negative? We don't need the number. So I can see here that basically we're going to have a positive number times a negative number times a negative number. That, all in all, gives me positive times negative gives me positive. So that tells me my gradient here is positive. So stop the video, have a go at testing those other 3 regions and see what you come up with. All right, how did you go with that? Hopefully you've picked some points in each region, and we came up with a positive here and a positive for in between this region, a negative and a positive. So let's now think what that means. Positive gradient means it's going up. Then we're going across at a horizontal at our stationary point. Then it's going up again. Now we're getting a stationary point, and now it's starting to go down again. Hits a stationary point, going up again. So here, in this region here, we've got our stationary, horizontal I mean. So we've got our horizontal point of inflection, P point of inflection, POI. Here we're going positive, hits the top and then goes down, so we've got a maximum, and coming down, hits a stationary point and goes up again, we've got a minimum. Alright, if we actually go ahead and graph this, this is what it looks like. So here we are, I've just done a limit restricted domain. So here we are going up. This point here, we've got our horizontal point of inflection that we spotted at 0. Then at 2, we have our maximum, it's a local maximum. And at 4, we have our local minimum. And if we think, what's our global maximum? This is our global maximum because that's the highest value it gets to. And this endpoint here is our global minimum. So when you're coming to graph or sketch these, the critical points we've done so far is we want to find maxima, minima, endpoints of the domain, and later we're going to be, and of course we're going to look at x-intercepts and y-intercepts. So hopefully you've got a better understanding of how we can sketch curves by using the first derivative and then coming up with our sign diagram and interpreting your sign diagram. So thanks for listening, and if you've got any questions, bring them to class.